All right, so let us begin. Last time we talked about sequences and convergence and divergence and boundedness of the sequences, and then we talked about some of the properties of the convergent sequences, actually the relationship between boundedness and convergence and all those things we did. And then I wrote down a theorem. Basically, it talks about the addition of two convergent sequences, the multiplication of two convergent sequences, and the division of two convergent sequences. So I will try to prove some of them. So the first of those results is about addition of two sequences, right? If xn is a sequence that converges to L and yn is a sequence that converges to M, then we have to prove that the sequence xn plus yn will converge to xl plus M, right? So that's something we have to show, right? So there's nothing big, just so given xn converges to L, right? So I use the notation xn arrow L, that means xn is converging to L, right? So for every epsilon positive, there exists n1 belongs to natural number such that, okay, xn minus L is less than epsilon over 2 for all n greater than n1, right? So that is the definition of xn converges to L, and then yn converges to M. So again, for every epsilon positive, you say there exists some n2 belongs to natural number such that yn minus L is less than epsilon over 2 for all n bigger than n2, right? So you have xn converges to L and yn converges to M. So you write down the definition or epsilon delta epsilon interpretation of that limit, right? Okay, so now what you have to do is you have to combine both of them. You have to combine xn plus yn, and you have to see it should goes to, sorry, this one and no. You have to say this x plus xn plus yn is converging to L plus M. That is what you have to show. So, but unfortunately, one result is true for all n greater than n1, and the other result is true for all n greater than n2. So you have to combine both of them. So if you want to combine both of them, we did similar thing last time also. Right, so we choose n be the maximum between n1 and n2. Right? If n is the maximum between n and n2, then for every n greater than n, okay, so for every n greater than n, we have to we will say that n greater than n1 and n greater than n2 because n is the maximum of both n1 and n2. So therefore, those two inequalities hold for every n greater than n. Right, so you take xn plus yn minus L minus M. Right, so if you take that, right, obviously this is this. Okay, so you can see that xn minus L plus yn minus M, and you know triangle inequality. So this is equal to xn minus L plus yn minus M. Right? That is because of triangle inequality. But because n greater than n, so n greater than n1, n greater than n, so n greater than n2. So this one is less than epsilon over 2. The other one is also less than epsilon over 2. So both of them are less than epsilon over 2 plus epsilon over 2, which is. So this shows us that so for every epsilon positive, there exists n belongs to natural number, such that xn plus yn minus L plus M less than epsilon or all n bigger than n. Okay, so that shows you that the limit of the sequence xn plus yn is L plus M. So clearly the sequence is converging, and right, and its limit is L plus M as well. Right, so that completes the first part of the proof. Right. And the second result is similar. Right, so I leave that part as a homework. Right. Right, similar argument, same n, everything up to here is same. Right? For the same n, you can easily see that xn minus yn minus L minus M is actually less than epsilon, right? Similar kind of triangle inequality will come, right? So you can easily see that it's just triangle inequality, and that says this is less than epsilon, right? So from this, you can also prove that xn minus yn will convert to L minus M as well. Right. So in the first convergence results, we put plus or minus. Right. So for the plus, I write the full proof. Right. Minus is similar. Only difference is this triangle inequality. You do it for xn minus yn minus L minus M. Right. So all you need to do is to apply triangle inequality for that, and you will get that is less than epsilon because of all these arguments. Right. So you can equally show that the difference of two sequences will convert to the difference of limits. Now the third one, right? Xn times yn. Right, so that's slightly tricky. Right, so xn goes to L and yn goes to M, then xn dot yn will convert to M dot n. You have to prove that. Okay. So for that proof, right, we will do that proof. First thing, right, this statement we proved last time. If you have a converging sequence, right, and converges to a finite limit, then the sequence is bounded. We proved that last time. And only the converse is not true, but this statement is true, and we have the proof of that, right? So let us say that because yn is bounded, right? Since yn is convergent, it is bounded. So you can say definition of boundedness I wrote last time. There exists M, a positive number, such that absolute value of yn is less than M, or all n belongs to natural number. Okay. So this is how we define boundedness in the last class, right? So boundedness of a sequence, or less or equal. Okay, last time I took less or equal, so I will stick with that. So there exists a positive constant M such that the absolute value of the sequence components of the sequence is less than some capital M. Right. Now this is the first results we can obtain from what is given to us. Right. Next. Okay, so then it was given that xn converges to L and yn converges to M. So you can say that for every epsilon positive, right? So there exists n1 said that this time in place of epsilon I write epsilon over M plus absolute value of L. Right? M is given, M is something you find here because of boundedness. And L is the limit of the sequence xn, so that is a real number. So when you put absolute value, that becomes positive, right? So epsilon over M plus absolute value of L. M is strictly positive, so even if L is 0, it doesn't matter, right? This one epsilon over M plus absolute value of L is a positive number. So again, you have two different n's, n1 and n2. But you have to combine them. So the idea is to take maximum. Okay, so you choose n as maximum of n1 and n2. So now the thing is, you have to find this. Okay, xn times yn minus L dot m. This absolute value is what you have to compute, and you have to show that this one is less than m epsilon, right? So this value is less than epsilon. That is what you want to get. But what you have is xn minus L and yn minus m. Those are the things you have, and also you have absolute value of yn is less than x. So what I'm going to do is to so I add and subtract L times yn here, right? So xn yn minus Lm is what you have, but I add and subtract L times yn here, right? So I can now break it into triangle inequality. So this is actually, let's say, equal absolute value of yn and absolute value of xn minus L. That's absolute value of L and absolute value of yn minus L. Okay. So if you apply triangle inequality and other properties of absolute value, what you get is you get absolute value of yn minus xn minus L plus L times absolute value of yn minus L. Okay, so that is what you get. But absolute value of yn is less or equal to m, and xn minus L is less than epsilon over that. L is L, and yn minus m is also less than epsilon over that. So when you apply all of them, this is less than m times epsilon over m plus absolute value of L. Absolute value of L times epsilon over m plus absolute value of L. Right. So because yn is less than m because of boundedness, xn minus L is less than epsilon over m plus absolute value of L because of the convergence, and then absolute value of L is there, and then y minus m is less than m plus absolute value of L because of convergence. Right. So now if you simplify this, you know you will get epsilon. Right. Now you will understand why we choose these values here, right? Instead of epsilon over 2 or something, the reason why we put epsilon over m plus L, because here you get an m plus L here, right? So you want to cancel them. That is why you choose m plus L on the denominator when you write down the definition of convergence, right? So that is why always, depending on the final answer, you might have need to choose these values, right? So I choose these values because I already figured it out that this is how my inequality will look like, right? And suppose if I didn't choose, so suppose in place of here, right, if I just say epsilon, and if I just say epsilon, right, from here this is what I will get. This is less than m epsilon plus absolute value of epsilon. So this is actually m plus absolute value of L times epsilon. Right? So this is what I have. But I should have only epsilon here. So I have to divide by m plus L. If I have to divide by m plus L here, I have to divide here. That is what I did here and here. Right? So this is kind of a reverse, looking in the reverse way to figure out what you have to put on the denominator below the epsilon there. Right? So that is how we prove that. So now if you combine all of them, then you know for every epsilon positive, you know their x is n belongs to natural number like that. X in there by n minus ln. So that is what you have for convergence of the product of two sequences. Right? So if you have two sequences that are converging to finite limits, then the product will converge to the product of those two limits, right? So that is that result. Now the third part, division part, I leave it as an exercise for you because the ideas are same. So you try that proof on your own to see whether you will be able to figure it out or not, right? So extend converges to L and yn converges to M. So xn over yn converges to L over M when M is non-zero and yn is non-zero over M, right? So this is the third result we write down earlier, right? So the idea is same, right? So you can use boundedness. At the same time, you can use the other properties as well, right? Try to figure out the proof of this. Try this proof as a homework. Figure out whether you will be able to do the proof. Right. Now, I will write down a couple of more exercises. Right. Again, these are properties of the convergence of sequences. And the first result is if xn is a converging sequence and converges to a finite limit L, then right, the absolute value of the sequence will converge to the absolute value of the limit. And so that is the first result. Second part is right. So the first result is about absolute value of the limit, right? So limit of the sequence and the absolute value of the sequence, whether they both converge to the same way. And the other one is about the limit of a sequence with positive components, right? If all the components of the sequence are positive and if they are converging, then the limit will be bigger or equal to 0, right? So these are two of the exercises. And so I will just give a hint of how to do these things. But now proof idea is always same. The way you write down the proof is going to be similar to what we have done already. Only thing is just to see the scratch here. So let me write it down. Okay, so you know xn converges to L gives you xn minus L is less than epsilon for all n bigger than n, right? So I skip a lot of things because you already know that what do we mean by for their x is epsilon, etc., etc., etc. I'm skipping those lines, right? But at the same time, you know that triangle inequality You know this, right? Absolute value of xn minus absolute value of L, the whole absolute value of the whole thing is less or equal to x minus L, xn minus L absolute value. That is from the triangle inequality, right? So you know that this is from the one part of one sequence of a triangle inequality. So if you combine this and this, then you will get absolute value of xn converges to absolute value of L. Right? So this is the hint. Hint for exercise number 1. Right? So you choose xn goes to L, or you take xn goes to L and then write down the definition, but you observe that by triangle inequality you get this xn minus L is less than xn minus L absolute value. So the rest is as follows. The second part, right? And you take L is equal to the limit of the sequence xn, right? And given xn is positive, right? With xn is strictly greater than 0 or length, right? So you want to show that limit is bigger or equal to 0. So order property, you studied that there are 3 ways that you can relate a number. One is it is bigger than 0, equal to 0, less than 0. Those are the 3 possibilities, right? But what you want to show is greater or equal to 0. So it cannot be less than 0. So again, by contradiction, you choose. If L is less than 0, right? You assume L is less than 0, then you know minus L is bigger than 0, right? You know minus L is bigger than 0. So you can choose. So you can choose epsilon as minus L because that is the positive. Epsilon can be any positive number. So you choose epsilon is equal to minus L because minus L is positive, right? But because this is the limit, you have this, right? Xn minus L is less than epsilon. So this gives minus epsilon less than xn minus L less than epsilon, right? So you have this kind of a definition for absolute value, right? So when you have x less than a, absolute value of x less than a, then you can write it as minus a less than x less than a. So basically, that is by removing the absolute value, you get this, right? So that means epsilon is minus L, so minus of minus L is less than xn minus L less than minus L. Okay, we have this. So this gives you 2L bigger than xn less than 0. Right, so if you add L on both sides, here you have already 1 plus L and then another plus L, so you get 2L less than xn minus L plus L, so xn, and then other side you have a minus L plus L, so 0. So what you have is xn less than 0. What we have is, what was given is xn bigger than 0. So both of them are not possible, right? This and this cannot happen at the same time. So this, here you get a contradiction. So this one is wrong. So it is bigger or equal to 0. Okay. So that is how we prove the second part. And so I just give you the scratch of the proof. You can write it in a proper way, right? So just the hints are given to you. And so these are again a couple of other properties of convergence sequences. Okay. Now let's go back to the first example, the first exercise. The first exercise that we see is if the sequence converges to a limit, then absolute value of the sequence converges to the absolute value of the limit. Will the other way around works? Right? So I will do that again, another exercise. Or remark. Right, so you have absolute value of xn converges to absolute value of L if xn converges to L. Right? Right? Converse is not true, but the converse is not true. Right? Because that means that is absolute value of xn converges to absolute value of L cannot implies xn converges to L. Right? So the converse is not true. So if I want to disprove something, that means if I want to show that converse is not true, then obviously I have to give an example. Okay. So I have to give an example means I have to give an example of a sequence whose absolute value has a limit, but the other one does not have a limit. So counter example. Again, very famous example which we studied already, -1 to the power n. Right? Xn is -1 to the power n. So you all know that absolute value of xn is 1. So the limit is 1. Right? You all know that absolute value of xn is 1 because -1 to the power n absolute value is this. So that's the limit. But you already know, or we already proved that limit of this sequence does not exist, right? So this xn will oscillate between minus and plus 1. So there will be no limit exists or no finite limit exists, even infinite limit. The limit does not exist for the sequence -1 to the power n. So that is the counter example of this result. Okay. Now this is about convergence and another results about convergence and the absolute values of the sequences. Now what we are going to do is we are going to move into another important property of convergent sequences known as sandwich theorem. And so you all know what we mean by sandwich, right? So it's made out of bread, where you have two bread pieces and some stuff of either potato, meat, or fish, or fish, or whatever stuffed in between, right? So you know that you know the meaning of sandwich, right? So you have a bread piece like this and bread piece like this, and you have two bread pieces up and down, and then you have put some stuff in the middle and put it like this, and that's called sandwich. Similarly, we have a similar kind of approach in sequences, right? So what you have is you have a sequence here, and then you have a sequence here. Both of them converge, right? If both of them converge to, then any sequence in the middle between these two will also converge, right? So that is called sandwich theorem. So you write this as a theorem. The name is sandwich theorem, so you should remember the name. right? So it's called Sandwich theorem. So here you will have three sequences. So here's the sandwich thing. You have three sequences, right? One of them is sandwich in between the other two sequences, right? If xn comma yn converge and if both xn comma yn converge and converge to the same limit. Okay, so if the sequences on both sides of the sandwich are converging and converging to the same limit, then the sequence in the middle will also converge and converge to the same limit as well. Right? So let us do this proof. Right? So it's not a big thing, very similar to all. Right? So you know xn goes to L. Right? So you have xn goes to L. So there x is n1 belongs, so let epsilon positive. So you always start with an epsilon positive. So here I put epsilon positive in the top, right? There x is n1 such that xn minus L is less than epsilon over 2 maybe. What doesn't matter, I can put it as epsilon. Let's keep it as epsilon. 4 more n greater than n1, right? And then you have yn goes to L. So there x is n2 belongs to natural number such that not yn, no, zn goes to L. Because the sequence on both ends such that zn minus L is less than epsilon 4 whole n greater than n2. Right, so this is what you have. Right, so by the convergence of xn to L and convergence of zn to L, this is what you have. Hello? ನಾನು போயல தானே இல்ல நான் சும்மா இல்ல ஜூம்ல சும்மா ஆன் பண்ணி போட்டு போய் தெரியா okay, so this is what you have. So now you have again two ends, n1 and n2, so you have to combine both of them. So the idea is always maximum of n1 and n2, right? So you go for the maximum of n1 and n2, right? So here's the trick. For all n greater than n, you have xn minus L is less than epsilon. At the same time, Zn minus L is also less than epsilon, right? So this is something you have here, right? But what you want to get yn minus L is less than epsilon. So you have to get to yn minus L. So how do you get this is here? First, from this, you can see this, right? So this is L minus epsilon is less than xn less than L plus epsilon. And if you remove the triangle, if you remove the absolute value, right, then you get minus epsilon less than xn minus L less than plus epsilon, right? And then you add plus L on both sides. So you will get L minus epsilon is less than xn less than L plus epsilon. Okay. So here also, if you get rid of the absolute value, you will get L minus epsilon is less than Zn is less than L plus epsilon. Okay, you have these two results. For all n bigger than n, you have this. But you want yn, right? So you want to get yn, and yn should be between L minus epsilon and L plus epsilon. That can be easily done because so we will take piece by piece. Okay. So what I'm going to do is I'm going to take this piece, right, and then this piece, and then this piece. I'm going to use the three pieces I circled by green pen. Okay, this is given. This is from the convergence of xn, and this is from the convergence of zn. So I can combine both of them. So I will start with the first one. So what I have is L minus epsilon is less than xn, right? But this says xn is less or equal to yn. So xn is less or equal to yn. And again, it says it is less than zn, less or equal to zn. So less or equal to zn. But this inequality says zn is less than L plus epsilon. This is less than L plus epsilon. Okay. So now this and this gives you L minus epsilon is less than yn because here it is strictly less than, right? And less than L plus epsilon. Okay, so you have L minus epsilon is less than yn less than L plus epsilon. So if you interpret this here, so you get minus epsilon is less than yn minus L less than epsilon. So if you subtract L from both sides, you get minus epsilon less than yn minus L less than epsilon. Okay, so this is basically what absolute value of yn minus L is less than epsilon. Okay, so what do you have? Arbitrary epsilon, there exists n such that for every n greater than n, yn minus L is less than epsilon. And so what you have for every epsilon positive, there exists n belongs to natural number such that yn minus L is less than epsilon for all n bigger than n. So by definition, it says limit of yn will convert to L. Right? So this sandwich theorem becomes very handy when it is difficult for you to find the limit of a sequence. Right? Whenever it becomes difficult for you to find the sequence, limit of the sequence, you may apply the sandwich theorem because you can put two sequences above and below that converges to the same limit and put the unknown sequence in the middle, then you can easily see the convergence. Right? Say for example, Okay, here's the question. You have a sequence of 1 upon n factorial, right? So you studied factorial. I am not sure whether you studied factorial in A level or not. You must have studied because you studied permutation and combination in A level. So you must have studied factorial, right? So if I say 5 factorial, that is 5 times, 4 times, 3 times, 2 times 1. And so that is factorial. So we do that. Call it 5 factorial. So actually n factorial is actually n times n minus 1 times multiplied by 2 times or 3 times 2 times 1, right? So that is what we mean by n factorial, right? So you must have learned this in A level when you study combination permutations. So 1 upon n factorial, they ask you to check whether this sequence will converge or not. And if it converges, then they ask you to find the limit. So here I am going to use the sandwich theorem. Because 1 upon n factorial is bigger than 0. You all know that, right? Because n is a natural number. So 1 upon n plus 1, n minus 1, n minus 2, all the multiplications. But it is still bigger than 0. That you all know. 1 upon n factorial is bigger than 0. You all know, right? For any n. And it will be always less or equal to 1 upon n. For all n belongs to natural number, because you all know if n is 1, it is 1 upon 1 factorial. It is 1 and 1 upon n is 1, so they are equal. If n is 2, that is 1 upon 2, 1 upon 2 equal. If n is 3, that is 1 upon 6. The other one is 1 upon 3, so 1 upon 3 is bigger, right? So you can easily check that 1 upon n factorial is smaller or equal to 1 upon n for all n. So this is some results you can write by using your very basic mathematical knowledge about numbers, especially natural numbers. So clearly, this is 0. You all know that, right? So 1 upon n, limit n goes to infinity is 0. We prove that also. So that's 0. So this sequence goes to 0. This goes to 0. So both of them has a finite limit. So by Sandwich theorem, because both sides converges and converges to the same limit 0. So the middle sequence will also converge and it will converge to the same limit 0. So this is the application of Sandwich theorem. So you can apply Sandwich theorem to see the limit. Similarly, one upon 2 to the power n. Right. So similarly, as a homework, you check whether the sequence 1 upon 2 to the power n will converge or not. If it converges, what should be the limit? Right? So you can apply Sandwich theorem to this again to see the limit of the sequence as well. And so that is about Sandwich theorem, which can be again used to find the limit of a sequence. So I'm going to stop here, and in the next class, I'm going to talk about a little bit more about the properties of Sandwich theorem, and then I will talk about another type of convergence of a sequence. Right. So I will stop here and continue on Monday morning.